Hello and good morning, everyone. My name is Miguel Lopez. I am your first presenter today. I'd like to start off the morning by thanking each and every one of you guys for joining us today for our capstone presentations. It means a lot to me, and I know it means a lot to each one of my classmates that you took the time out of your day to be here and to allow us to present our final projects. So with that, let's get started. So today I'm going to be talking about triangulation of sound. And what that means is basically being able to detect a specific sound and triangulating its precise location in a x and y coordinate plane so we can visually see its exact precise location. Okay, so here's a table of contents. Um, so today I'll be talking about the certain components that are required for this project to work, the math behind it. Also, I'll be showing you a few of the schematics and the fitting diagrams so you're able to see how it actually looks on paper and what relatively looks in real life. And then I'll be showing you guys a quick demo of the final projects to show you guys that it actually ended up working.
Okay, so the inspiration for my project. The city of Albuquerque actually inspired me to do this project. They were the ones that came in to speak to us as a guest speaker for one of our weekly guest speakers. And they spoke about wanting to make the city of Albuquerque, a smart city. And to me, that's great. I know Albuquerque has a lot of ways to do that. And they gave us a lot of really good ideas of what they have already done and are planning to do. And one of them had really stood out to me. And that one was, they wanted to detect car accident sounds to be able to know where it happened and, when it happened so that they can, get appropriate authorities, ambulances, firefighters, anyone necessary to get to that specific location. And that really, stuck with me because to myself, I've been in car accidents and I know everyone else has. And to be able to have that assurance of being able to get help, the appropriate help in a good amount of time is something that relieves everyone's or eases everyone's minds about that. So with that, I decided, well, I can change this to, gun safety. There's a lot of gun violence throughout our country, and we want to be able to have a safe environment for everyone anywhere you go. So that's something that I wanted to pursue, and that's exactly what I did. And let's start our journey. So our objective was basically to create a device that can detect a sound, and this sound needs to be specific. It can't just be, someone clapping, yelling or anything like that. It needs to be a specific sound that when it's activated, it does the job necessary. And with that, it also shows the location where it happened. So in order to do that, we need to acquire 3 microphones. We need I added an option to utilize NeoPixel strips to show its location when it happens. So it'll be set up as a Y and X coordinate plane. If you all remember that from algebra in high school or something like that. It's basically on a quadrant of X and Y values. Also, we're going to be recording and logging data to an SD card reader. This is going to be used for sound waves in particular, which I will explain later on in the slides. And then we're also going to use the particle argon clash dashboard. This is to log all the sound detection readings that we get. So instead of having it to write to the SD card, we can actually see it live from the website itself, what time it happened, where it happened, and it'll just keep that data for us to see, in the future to be able to interpret it in any other way we want. So the math portion. This was probably the hardest part of the project because it's math. Not everyone's good at it. I'd like to think of myself as a decent person at math, but going back to equations of stuff was a bit hard. But with the help of Brian and the knowledge of math, I was able to do it. So this is the equation of a circle. I'm sure most of you hated this thing if you saw it or enjoyed it. Math is amazing. But here you go. That's what it is. This is basically the basis of our math for this project. As you can see on the right, we have a picture of the city Albuquerque Civic Plaza. This is where the project is based off of where to detect these sounds. And as you can see, 1, 2, and 3 are microphones that are placed throughout the city. Um, on a smaller scale, we have it on a board here, um, have a picture of it, of the Civic Plaza, and you'll see that in a bit. And what T1, T2, and T3 are, there are the time difference of the sound traveling to these microphones from point 4, which is where the sound happened. You can think of it as the time or the distance it traveled, but today we're using it as the time value. So these are the three formulas that we came up with from the equation of a circle. As you can see, we derived it to have three unknowns, which is t, x, and y, and that's what we're going to be solving for today to be able to get t is the time distance of the sound that it traveled, x and y are obviously the coordinate points of where it happened, so we can precisely know the location of it. And then a and b, as you can see here, are things that obviously we don't know. And as you can see in the picture to the left, we have B and A. These are basically the distance from T2 and then the microphone here itself. So we're trying to calculate distance in order to be able to find that precise location. And that's what B and A are used for these mathematical equations. So here's a little snip of the code that I programmed. It's the timing code. And what this does basically is gets our values for each of the microphones, named values 1, 2, and 3. And this threshold is a specific threshold that we set up in order to detect a sound so that not random sounds are detected. You know, a high-pitched, one solid sound is picked up. And once that happens, these these if statements pick up that sound and then start timing it. So once it reaches this microphone, and this microphone, down here it displays all that data, and we know the time difference from each and every single one of the microphones and how long it took to get to each specific one. And up here we just add a delay of 2 seconds in order for the system to, you know, give it time to get rid of that sound that just happened in order for it not to give us bad readings. And then up top as well, we set T1, T2, and T3 to 0 because we don't want it to keep adding on the same value. We want it to set 0 every time we, you know, get a new sound. And I'm not really going to get into depth about this, but this is basically the math that I did. Yes, it's 4 pages long, and I'm sure a lot of you won't understand what's going on. I hardly did either, but at the end of the day, it's what we need in order for this all to work. And the final result is these equations. So right here we have the A, B, and C values for our quadratic formula. And as you can see down here on one of the pages on the previous slide, it has this final result down here in one of the equations. So I just wrote them down here so you're able to distinguish what A, B, and C are. So once we have these values, we can definitely just plug it into this quadratic formula, which is set equal to T, so that we can get that time difference. And then once we plug in these values, we then get the value of t, and then once we have the value of t, we plug in to our x and y equations, and once we solve that, we get our coordinate of where the sound actually happened. So right now I'm going to be speaking about the components we used today. I'm not really going to go into depth about them. I'm just going to explain what they did and how they helped in the project. So the particle argon is the microcontroller that we are, as a class, are using for our final project. We are only using one today. It powers everything, so it's very handy to have. It has Wi-Fi and Bluetooth capabilities as well, so we can connect to the internet without having to, you know, be plugged into our computer or anything like that. So these are the electric microphone amplifiers. There's a set of 3. I used 3 of them, and these are used to detect our sound. And as you can see in the picture, they are screwed into little wood blocks. And the reason for that is because I initially wanted to, 3D print little light poles, but I came to learn that the light poles would be, a certain material that if you try to screw it in, it break it apart. So I just thought, well, little wood blocks would help. It holds the microphone in place so that it doesn't move around. So we will get precise readings, because initially at the beginning of the project, I didn't have them mounted, and we would get weird readings, and it wouldn't be as precise as we wanted it to. It would work, but it wasn't what we wanted. So this is something I implemented to make it more precise. This is a micro SD card that we'll be using today. We're using one of them. This is what we're going to use to catalog and be able to read all the data of the sound waves that we pick up later in the project. So yeah, NeoPixel strips. So what these strips are basically doing is showing us where the sound happened. There's 2 sets, X and Y axis. There's 31 pixels on both of them. So whenever the sound is picked up, you'll be able to see with the light indicators of the NeoPixels where it happened. Okay, so these are my schematics for the project. Up here are the 3 microphones wired into where they need to go, power, ground, and the input pin. Right here, we have the micro SD card reader. And then down here, I have 2 single NeoPixel um, components, because I didn't want to have to wire 31 or 62 NeoPixels. So I just did one for each of the strips that we're going to be using today. And for those of you who not necessarily can't read schematics, but can visualize it, here's a fritzing diagram of what is actually wired in and how it looks in real life. So we have the 3 microphones, excuse me, the particle argon, the SD card reader, and the 2 NeoPixel strips, but here are the 2 single ones. And this is our work in progress. So these are just a few pictures of what I was doing throughout the project. Here is gluing down the little blocks of the microphones. Down here we have Brian talking to me about how to clap in a certain location to be able to diagnose where it actually happened. And here you can see that some NeoPixels are lit, and this was just a little error that I didn't implement into the code. But after I figured out what had happened, we were able to clear out the pixels every time a new sound was detected. And then up here, you can barely see it, but here I am soldering these long wires to the NeoPixels so that they go along the X and Y axis where the microcontroller is connected down here. And here I have a short little video of, finally getting it to work. Yeah, so I was surprised it worked. I'm sure you could catch that in the video audio, but it was a long, hard week of working, and being successful, meant a lot. So here's the actual demo video of my project working. Okay, so that was part 1 of my project. So initially I had set up a few parts and to be able to complete and improve the project on its own. So basically part 1 was just exactly what I did right now. being able to triangulate the sound, show it visually with NeoPixels so that everyone can actually see where it happened. So as you can see here, by comparison of these two pictures, we can distinguish that it's pretty precise of where the actual sound happened. So here's a clap, here's a corresponding NeoPixel lighting up for both of them. And as you can see here without the hand, it's pretty much precise. So we know it works, it's precise. And, I'm very proud of myself, and to be able to do this was amazing. For the coordinate points, we had ranged it from 0 to 1 initially. And as I will be talking about in a minute, we wanted to make it more precise. So here is our part 2 of our project. So what this entails is that I finished the project. I wasn't sure what else to add. Spoke to Brian about it, gave me great ideas, and we decided to implement actual GPS coordinates of where it actually happened. So let's get into that. So this is one of Brian's devices that he let me borrow. This basically just shows the GPS coordinates of where you're at or standing around anywhere in the city or basically anywhere in the world. Up here is just a battery pack, and here's a little GPS unit. So down here is a little OLED display that shows you the time, longitude, latitude, elevation, and I believe it was pressure. I can't remember the other one, but this is pretty accurate. So this is what I use to actually go get the GPS coordinates of each of the microphones. And as you can see here's one microphone, here's the other, and the other one's up here. So I actually went to the Civic Plaza, stood right in that exact spot and got that coordinate. And I did the exact same thing with each of the other microphones. And I got those coordinates and was able to map it to our current map function from 0 to 1. So I ranged it from 0 to 1 to the GPS coordinates of each of these microphones. And then you'll see that using the particle argon clash dashboard, it logs every instance happens. So like here you have the noise. I named it noise. So when clapping happens, it picks it up, the time it happened, and the date. And then on the right, you can see that it gives you the precise longitude, latitude coordinate of where the sound actually happened. So as you can see, as if you give the coordinates to the Google Maps, you get this exact location. So we know that it's precise with GPS coordinates as well, which is amazing, and we know that it's at the top of the line. We also added capturing sound waves to the project. Initially, that wasn't my intent, but since I finished early, I was able to add on things. So this is something else I added onto it. Up here, you see 3 sound waves that we captured. Up here, you have a dog bark, an assault rifle gunshot, so several gunshots, and then a car accident. That doesn't look like anything, but that's what it sounds like. So in order to be able to pick that up, this is a code. Not sure if anyone will be able to understand this, but basically what this code does is it starts reading the data and capturing it into a 2-dimensional array, which captures the amplitude of the sound and the timestamp of when it happened. So you'll see like an array of the timestamp and then the amplitude of the values going, down the line of the Excel sheet that we are sending the data to. With that in mind, so whenever value 1 is greater than the threshold, so whenever you clap, it'll start doing this for loop, integrating our array size. So it'll start picking up 1,024 data points, and then it'll start logging the time it took. Also, this 500 is corresponding to microseconds. So if every 500 microseconds, I want you to collect a new data point. So that's what that's for. So then we're just displaying the time in micros, we're getting the microphone values, and then we're adding them to our sound wave array of the 2-dimensional that I was talking about earlier. On the right here is what we're doing to write to the SD card. So it's basically the same concept, but here we're actually sending the data to the SD card. So that's basically it. We're just sending the actual timestamp divided by a million. This basically transitions from micros to seconds so that we're able to actually read the data in seconds, not in microseconds, which is a really big number. So that's basically how we did that, and we're able to implement these two things to the final project. Okay, so some of the challenges I had for this project was obviously understanding the math. You know, remembering the circle of equation, that was really hard for me in high school, so I can only imagine, you know, now. But you know, with practice and having good guidance, you're able to understand what's going on and solve these equations. Also, solving systematic equations, that's basically the basis of the math as well. That was pretty hard for me in high school from what I can remember, but here it wasn't too difficult. If you can actually see behind me, this is a board of math. You can't really see anything, but it's just math up there. But I transitioned it to the pieces of paper that I had at the beginning of the presentation. Also, PEMDAS, I'm not sure if any of you know what PEMDAS is, but it's basically the order of operations. So when you're doing math, you want to do math correctly. You don't want to just add, subtract, multiply, divide random things, because if you don't do it right, you're not going to get right values. PEMDAS is basically P for parentheses, E for exponents, M for multiplication, D for division, A for addition, S for subtraction. So you want to do this in every math equation or math solving that you're doing to be able to get the right answer. A second challenge I had was distinguishing the data type to use. This was, you know, I think I was, you know, talking to Brian about it, and it's probably my kryptonite when it comes to coding. It's generally when I try to use int and floats. Um, so whenever I didn't use the appropriate data type, it would result in inconsistent readings. We'd get zeros where we weren't supposed to get zeros. We'd get really big numbers when we needed 0.0 something value, you know. So being able to distinguish that is probably a challenge that I have and will probably have in the future. But excuse me, but it's something that I can work on and know that I will understand someday. And it's something I understand now. It's just, you know, it's when to use it. And future goals for this project, I definitely would want to detect specific sounds, uh, generally frequencies. You know, so you want to be able to record the frequencies of gunshots, car accidents, so that you're not picking up random sounds and, you know, logging that hundreds and hundreds of sounds, you know, that you don't need. So in order to be able to detect these frequencies and sounds, you're able to distinguish what you actually want to pick up and what you don't want to pick up. I also want to be able to implement it to a big city. You know, Albuquerque is a big city in the state, but we do want to, well, I do want to implement it somewhere where, you know, it's heavily have crime rate with gun violence and stuff like that. So that is my future goal for that. And I definitely want to be able to alert appropriate authorities whenever an incident happens. So whenever the sound is picked up, I want to be able to send, you know, a text or a call to the appropriate, you know, police department, fire department, anyone in the area to let them know, hey, this happened. And if someone calls it in, you know, you already have that data. So you're able to, you know, go off of, instead of, you know, someone calling in saying a gunshot happened 3 miles from my house. You know, you'll actually know where it happened, and if someone calls it in, you'll have that data at hand. So that's going to be it for me today. If you have any questions, feel free to ask me. I will try to answer all of them.